All right. Does it say? They're thinking we're live. Are we live? Are we live? I hope so. Because it's been a minute. Let's see. Make sure that we actually are going. It's always funny. Looks like we're going here, and it is a good Monday for sure, everyone. This is going to be a fun little class today, and being more of a class type, I've got into professor mode. Right? We're teaching some cool stuff today. Drives 101. So here we go. I put on a jacket today, but it's not a suit jacket. It's actually a sport coat. It's funny stuff. I know. I am an engineer, not a comedian. My name is Jason Watts, and I am Drives in Motion guy, person. I've got about 25 years of experience working with Siemens motion control technologies, and about 10 of that was with a Siemens electrical distributor as a drives and motion application engineer. So during that time, I did quite a few of these little classes, and I am it is great to see everyone coming on, and so everybody coming into chat, great to see you. Good evening for those that are on the that side of the world. That's awesome. My wife is actually from Southeast Asia, so when we're over there, or I guess her family's from Southeast Asia. She's from Georgia, but the state Georgia, not the country. But yeah, we are going to be doing some cool drives technology, just basic class, and I feel like that is loud in my ears. The music's too loud. Let me know, because going through some pretty cool stuff today. Yeah, I was kind of telling you a little bit about myself. If you are new to the stream, new to the channel, welcome. It's awesome we are always doing some cool drive stuff, mostly centered around Siemens technology. But today we're going to be talking about stuff that kind of applies across the board and to a lot of different drives. And then we're going to go kind of the second half of the class, we'll call it. We will be doing very specific about Siemens, how to set up a drive, how to get it communicating, how to actually do the programming, some of the concepts in some of the communications with ProfiNet. And some of those technologies, or some of that kind of discussion is available kind of like at different other manufacturers. So you might be able to use that if you're using like a Yaskawa or Mitsubishi drive or something like that, Omron, those sorts of things. But I know they work with Siemens. We're going to be using Siemens TIA Portal version 17. They are up to version 19, but I also understand that everybody is not always up to the latest and greatest. But one of the things about me that I didn't mention before is, well, I have all of that experience with Siemens technology from kind of throughout the years. Now I actually run CEO and founder of a little automation company out of the southern U.S., the heart of Dixie, Alabama, and we do a lot of agriculture work. We also do machine design, so OEM equipment design we've got some roofing products out there that winders, accumulators, things to really optimize the production side, and we're doing the mechanical and electrical design for that. So we also are a gold certified integrator, but I don't do gold certified ignition integrator. Our company is Alpha Industrial Technologies, and that's mainly through one of our other business owners. His name's Brandon Hughes, and he does excellent work in ignition. And so yeah, maybe eventually I'll be able to get him on, but he's just always doing awesome stuff with ignition. And so maybe I'll get him on and we'll do some ignition stuff on this channel as well at some point. But yeah, thank you for joining. If you're joining in the stream, be sure to like the stream to get it out there. We're going to be going for a couple hours today. And so come and go as you please. But if you're coming in and you're watching this on demand, drop a comment, say, hey, and if you're not subscribed and you're stumbling across this, take a look at the rest of the content that's on this channel. We do automation stuff. We've also started doing some mechanical design stuff, more of just kind of like laid back, basic introductory 3D modeling and design, because we realize that in the automation world, you kind of end up having to do a lot of everything, a little bit of everything. And so having a good background in your mechanical design is going to help you a long way when you are working with your automation system. So without further ado, we're going to start talking about kind of an introduction to drives today. And if you noticed in the description for this stream, I dropped a little shameless plug for a little book that my dad, so 99% my dad, and then I go in and add in a little bit. We worked to write these books, and this is the first in a series. It's available on Amazon, and we're going to be going through some of the topics that are in about half of this book. This particular one that's linked in the description goes through motors and drives, AC motors and drives, and we're going to be talking about the kind of AC design things. And this book is kind of like a go-to on kind of a reference source, and like if you're new to automation, you're definitely going to get a lot out of this. But if you are kind of like been working around automation for a while and have kind of like a maintenance background, this is going to fill in those gaps of, hey, here's here's what I've seen and worked with for all these years, and here's the kind of like engineering technical reason behind it. And so that's what we're going to be doing today. And it's essentially, we're going to be covering the topics, not in full. That's in about half of this book today. So if that's something of interest, it's available on Amazon, and we're going to be coming out with some other ones here that are already in print. I just have to, already done in terms of like everything. I just have to get them formatted and everything onto Amazon, which is kind of a pain. But yeah, so if you are not familiar with what an AC drive is, or an AC motor and drive is, kind of wonder why you're on the stream. But joking. If you're not familiar with what it is, like, welcome, because we're going to be kind of stepping through the basics to kind of like get you off the ground. We're going to be talking a lot about induction motors and AC induction motor drives. Specifically, later on, we'll be talking about the G120 in the Siemens line. It is a general purpose induction motor vector control drive. And so industrial motors come in a lot of different flavors, but a lot of what you see out there will be what's called asynchronous induction motors. And we talked about a lot of those in depth in, I think it was a couple weeks ago. I did a stream about industrial motor sizing, and I talked a lot more about the motors themselves. So if after the stream you're kind of like wondering a little bit about the AC motors, be sure to check out that stream. It's got a lot more information kind of about how to size them, how they kind of work, and things like that. We're going to kind of skip over that, and we're going to talk mainly today about the drive technology. And the first thing we're going to kind of do, just like a quick reminder, I'm going to clip over to my sketch pad here, and we're going to kind of go through here, and we're going to kind of talk about what our AC motors, kind of how they act. Like one of the things that we talked about a couple weeks ago is an AC motor. If you have two parts of an AC motor. You have the part that spins, the rotor, and then you have the part that doesn't spin, the stator or stationary portion. What's up, everyone coming into chat? It's great to see y'all. Yeah, I'm glad tried to get a little bit more early in the US streams so that we can kind of get a little bit more from the earlier time zones, I should say. I say Eastern, the Eastern time zones. It's great to see everybody coming on, being able to be on live. So it's great to have you. So we're talking about the motor kind of construction, and I have a little motor here that I can show you. So when I talk about the rotor, this is going to be the part that rotates, and then the stator is going to be the stationary part, the part that you mount. So that's a little bit of our terms. Well, the thing about an AC motor, especially an AC induction motor, actually really all of them, is that if you run if this is frequency, so we'll call this, we'll just do it like this. So frequency. And the motor current, we'll call it, or torque, we'll call it this, torque. The current or torque at a certain speed, if you have a line frequency, so an AC line, so in the US that voltage is going to be 480, 60 hertz. Elsewhere in the world, it could be 400, 360, 380, 50 hertz. Like, it kind of depends. The big thing is the frequency, because the changing of the frequency changes how fast that motor turns. So we can kind of go through, and you can think about it like a 60 hertz signal will kind of might look like that, or maybe that's a 30 hertz signal, and a 60 hertz signal would be like that, something close. It's double. So the magnetic field in these motors is going to try and follow this magnetic field created by our line. So if we were to just put a AC motor, what's called across the line, we are going to have a situation to where you're going to have a fixed frequency. And so on the stator, okay, the stator will have a magnetic field that will be rotating at whatever your line frequency is. So in the US that's 60, most everywhere else in the world is 50 hertz. So we'll just call it I'm not as familiar with the 50 hertz stuff, so I'm going to use 60 hertz, but it's all linear. It's a linear equation. And so, like, base speed for a four-pole motor on a 60 hertz line is going to be 1800 RPM. I think that's 1500 RPM for a 50 hertz signal. But I'm going to use 60 hertz for all of this. The graphs will look all the same. It'll just be different numbers. And again, we go into depth in the motor, so I'm just going to kind of skip through this. But just as a refresher, if your torque will look something like this. And we're going to talk about this other side as well, because we talked about that as well. So at 60 hertz, this would be called synchronous speed, an asynchronous motor can produce zero torque. And again, this line is as the rotor speed starts to speed up. So as it kind of ramps up, it's looking at this motor torque. Okay? So that's how to interpret this graph. So as the rotor starts to speed up, it gets closer and closer to 60 cycles per second in this case, and it will move along this line, and eventually it will get up to 60 hertz. Well, in an asynchronous motor, you're always going to have a little bit of slip, because obviously there's going to be some friction. And so at some place along here, you're going to have a balance point, and they're going to rate that motor. And this will be kind of the rated torque, and this will be the rated speed, and then this is the slip. Okay. Again, we talked about this really in depth, but the reason I wanted to bring this up is because there's a couple of things. This is only for a fixed 60 hertz line. So if you were to take a big knife blade switch, I would not recommend doing this, by the way, or a contactor, and just throw a motor onto your line, that is how as this speeds up, this will be how much torque is available. Cool. Well, what a VFD does is it changes the frequency as seen by the motor. So the motor, instead of just seeing a constant 60, 50 hertz, you can actually vary the frequency of that motor, which means you can vary the speed, this speed here, you can vary that speed. So you can get rated torque at from 0 all the way up to rated speed. So in the US, this is going to be like 1750 RPM. On a 50 hertz line, this is probably going to be like 1350 or 1380, something like that RPM. So that's how your ratings work. So the way a drive does this is by making the motor think that it has a different line frequency. Okay? And so essentially what this motor is seeing is if we were to cut the frequency on the drive in half, say this is at 30 hertz, you would have a line that would be duplicated in exactly the same way, like that. And then essentially, you would just, at every point along the line, you would have this kind of effect here. Because as you're moving the line frequency up, it's going to have a different torque curve for every line. Okay, so if you average all of these out, you see you can find a point across all of these. So that's what a VFD does. It's really super cool. And again, there is a really in-depth discussion in our book here about this. And so you could see how it'll actually, it's probably going to whitewash it out. Can't see it. There's a page that really shows this drawing just straight up. And so and it also talks about if you are trying to run faster than the base speed, so this 60 hertz, this rated speed, if you were to try to run, say, 87 hertz, 87.5 hertz is actually a special number that we may not talk about, but you might see a lot of times drives running at 87.5 hertz. A lot of times it'll run in, you'll see it on crane applications, but you lose torque because your horsepower stays the same. And we're going to talk about why that is, because a drive can't create energy out of nowhere. And so it has to have a constant power. And so that's what we're going to be dealing with. But we're going to talk about that. So how does a drive do this? Let's clear this out and look at how a drive does it. Let's look at the structure of a VFD. So the physical construction of a VFD, what you have is a rectifier section, because over here you have AC voltage, right? Probably three-phase, maybe not. Okay, so you have a rectifier section. You have what is called a DC bus or DC link. It is a big capacitor or multiple capacitors. So this is DC. And then you have an inverter. trying to draw these things to where you can read them, but I will be unsuccessful because my handwriting is terrible. And then out here you have your motor, and then you have your three-phase connection. And so in these you can have different versions of like a rectifier, a DC link, and an inverter, but this is the basic principle behind all VFDs. Is you take AC, convert it to DC, and so this is going to be some sort of bus like this. If you're familiar with these, this is, again, talked about in depth in the book, but this is going to be some sort of three-phase rectifier circuit. You don't really need to know how this works. Just know that AC gets rectified into DC voltage, and this DC voltage depends on what type of rectifier you have and what type of line voltage you have coming in. So this is somewhere on the order of 600 to say 750 volts DC, okay, in this section. And that really comes up when we kind of talk about something later on. And that voltage varies, like I said, based on the incoming voltage and the type of rectifier that you have. So a couple weeks ago we did it was the last live stream. We talked about the SINAMICS S120 active line module, and so it actually can boost the voltage up on this DC link, and you'll see why that would be important here in a little while when we talk about some control modes and things. But just know every drive goes from AC to DC back to AC. And that is so that this inverter is essentially a controlled version of a rectifier, and then it will pulse in a way that we're about to talk about in order to trick the motor into thinking that it has a varying AC voltage or a varying frequency. Yeah, so if you're coming in on the live stream, be sure to drop a comment in the chat just to say hey, and hit a like, because hit the like on the stream so that it gets it out there to people. It's a matrix drive. No. Oh yeah, I'm sure, Lucid. There are some absolutely. Lucid brings up a good point. There are some drive technologies that uses different types of like phase shift technology in order to actually do different AC varying the frequency without doing this DC conversion, because the reason you would want to do that is you have losses here and then you have losses here. So there's another drive that I see this technology in. Ignatius, what's up? I seen you on LinkedIn. Like, it's good to see you on the stream. But yeah, so there's a drive technology that I see a lot in medium voltage drives, and there's one called the Robicon Perfect Harmony drive, and it's weird, and it doesn't use this it doesn't use this rectifier DC link setup. It uses these three-phase bridges. That's kind of like, it's really cool because you can actually hot swap. So you can lose some of the components and then hot swap out. I know it sounds crazy on a medium voltage. So these are like up to like 12470 volt drives. And so they're pretty cool technology there. But most industrial drives are going to be using this technology with your rectifier, your DC link, and then your inverter. So and until you run across an exception that this is the technology. And the reason why this kind of like thought really goes into the design of your system, because like that the Robocon Perfect Harmony setup, it does not have the issues that we're going to talk about later about pulsing, because this inverter section has some issues. So remember, we are taking a DC voltage and converting that, and I'm going to air quotes convert that into a AC voltage. So let's look at how it does that. So we're going to kind of zoom in on this inverter technology, okay? And if you're not familiar with how an inverter works, this is kind of the same technology that you would find in like a UPS, like a battery backup for your computer, because there has to be some form of DC to AC conversion in order for this stuff to work. Inverters for PV arrays, the same thing. This inverter section is not specific to drives. It just so happens that it's 3 phases, whereas a lot of other inverters out there will only be single phase. So in this kind of inverter, you're going to have on one side of it, we'll call it 650 volts, just to be kind of even, okay? Because remember, we've boosted this voltage up to 650 volts. And if you notice, that's a lot higher than 480 in the US or 400 elsewhere, maybe 380, whatever your motor is rated. That 600 volts is much higher than that. And so you'll sit there and kind of think like, wait a second, we're putting 600 volts onto a 480 volt motor. Yeah, that's why you have inverter duty motors, because technically you are putting 600 volts onto the windings of this motor. And so what you'll have is kind of your motor is over here. And one thing about a motor is there is what's called like an equivalent circuit diagram. So in the motor, you will have a inductance, and you'll also have some resistance, and then you'll have something that looks like this, and then you might have like a branch capacitance circuit, maybe something like that. There's a couple of different motor models, but the basic motor model is you have inductors and maybe a little bit of capacitance, but it's mostly inductance. Normally the capacitance is going to come in the cable, because this is going to be the cable resistance. This is going to be the actual winding resistance. And so if you have a really capacitive cable, like a shielded cable, you might put some capacitance in here as well. So this is mostly, though, it's going to be induction. And so the current is going to kind of smooth out, because an inductor resists changes in current, whereas a capacitor, like the big massive capacitors that we have on the DC link, resists changes to voltage. So that's kind of the circuit, the electrical circuit that is seen by this inverter. So just know that this is not just a resistive load. Oh yeah, we're definitely starting at the 101 level. We are taking class today, and hopefully I'll be able to remember the basics. Because this, if you don't kind of understand this concept, it's going to be very difficult to really kind of understand problems later on down the road. So know that this motor is going to resist changes in current and resist changes slightly in voltage. So we're going to clear this out. And remember, we've got our 650 volt DC bus here. And this is just, we're going to kind of look at the waveform, the voltage waveform as seen by the motor. And so this is going to be time. And actually, I'm going to do it like this. This is going to be time. So we're going along. And we would know that an AC waveform, if it were perfect, would look something like this, right? And this would, you would want this to be like 480 volts, right? So maybe let's redraw this and draw it something like this. This is what you're trying to get, where this would be 480 volts, okay? That's what we're shooting for. But all we have is this 600 volt DC, or 650, could be 650, 700, even 750, depending on what you have going on. And so this is what we're wanting, but all we're gonna do is we're gonna take, and all we have is switches. So like, think about it as like light switches, and we will turn the voltage on for a short period of time and then turn it off. Because remember, this, as the current starts to flow, that motor is going to resist that change. So it can't be instantaneous. So you're going to turn the 650 volts on, and then you're going to turn it off. And that's all we're going to do, is we're going to switch it in one direction, and then we're going to flip down and switch it in another direction. And the way that it tricks the motor into thinking that it has an actual AC waveform is it takes and does what's called pulse width modulation. And I'm sure you've heard of it, PWM. If you haven't, it's really cool. But it's kind of the core to a lot of technology and a lot of electronics, especially power electronics. So what you will do is when you're trying to create this kind of low cycle, you're just going to turn on it for a really short period of time. And then you're going to kind of wait. And so it'll kind of grow up, and then you're going to turn it on for a little bit longer. And I'm going to exaggerate this a little bit. And then you're going to turn it on for a little bit longer. And then you're going to turn it on for a little bit longer. This is a little off. And then you want it to start kind of going down. And so you will kind of do it. Oops, that was bad. Remember, all we can do is switch between our polarity, okay? But all we can do is turning on and off the 650 volts. And so think of the motor as averaging out that current and averaging out that voltage based on the inductance and the reactance of the motor. If you're not familiar with those words, reactance is when you have what's called inductors and capacitors in a circuit. It doesn't act just according to Ohm's law. So V doesn't always equal IR. There's a time component in there. And so because real things can't react instantly. So what we do now is we've kind of averaged out this upper part of the waveform, and now we want to switch over, and we will just do that same thing. So we can do a negative 650 volts just by changing the polarity of that voltage of that DC bus. And we're just going to do the same thing on this side. And as it kind of begins to do the same thing, and again, my drawings are not perfect, but I'm exaggerating it to make it, you get the point. like that. And so you see all we're doing is switching on and off 650 volts, 650 volts, or whatever our DC link voltage is, that DC, we switch it one way, and then we use this what's called pulse width modulation, and the motor itself averages out the current in the motor. So now all we would need to do is, if this were, say, a 10 hertz waveform, if we wanted to do 20 hertz, we would just shorten that up. We would just take these pulses and bring them in. And so all we would do is try to shorten up those pulses. And that's how you create this variable frequency waveform. So a couple of things that we'll just mention right now. You have what's called the carrier frequency, or the actual pulse frequency. This is kind of the minimum gaps between pulses. And so if you're cutting this like the time domain, if you're cutting this up into little pieces, how many pulses per second, that's going to be your carrier frequency. And so carrier frequency does not necessarily mean the maximum frequency of the converter, because if you are on like a 6 pulse or a 9 pulse or a 12 pulse, like those are all terms that you don't really need to know about right now. Your carrier frequency, the higher the frequency, the higher the maximum frequency that your motor can see, because you can chop up into different groups more. Now, there's a little problem if you have gone into any sort of frequency domain analysis, which is fancy, and you don't need to know it in order to work this stuff. But just know that, remember when I said before that nothing real can change instantly. And that is a principle that applies for voltage too. I drew this little pulse here, these pulses, as nice square waveforms, right? So I'm going from 0 to 650 volts instantly. Well, remember, I just said it, nothing real, so that capacitor that's in that DC link cannot change instantly. So what actually happens is this, there will be an effect called ringing. So like a ring, or like a bell ringing, and you will get a voltage waveform that looks more like you get these like pulses. And so every time you try to change instantly, you get this spike, because reasons. There's some like black magic, and there's stuff like all sorts of like Fourier frequency domain analysis and all this stuff, but you don't need to know that. Just know that if you try to change something instantly, it doesn't like it, because we're dealing with real things. We're not dealing with like math, numbers. And so when we try to do this waveform and change a pulse like this, it will pop up and then do like this, and then it will actually whoop, and then have these peaks. One thing to note is that these peak voltages can get really high, and what causes this is a combination of the capacitance of the cable and the motor, a mismatch, and the pulse frequency, the carrier pulse frequency. So how fast you are doing these pulses, chopping up the pulses. So the faster you're doing stuff, the more problems you can change. So just a word of advice, you want in terms of a process standpoint, you want your carrier frequency as low as possible, because this does more than just this like peak kind of problem that we're having here, this sort of stuff, it does more than just like damage your motors. It causes noise. It causes noise in the cable. It can radiate noise in your ground planes. It can create antennas out of shielding on your cables. So no one would put a radio, like a radio transmitter, inside of their control panel and expect it to work very well, right? That's why we ground electronics, we ground all these things. But this can literally, if you're not doing things properly, it can turn stuff into radio stations for noise. And so in Europe, there's EMC guidelines that are required for actually required, but that's probably not required in your area. So, but it can cause a big headache. But that's probably for like a 100 level class. But just know that if a manufacturer tells you to use a certain type of cable or to ground your cables a certain way, do it. They mean it. It'll save you a lot of headache. Siemens does a really good job about mitigating a lot of these factors, and if you're using a Siemens Drive, you can get away with what I would call lazy installations just because of the fact that they are a lot more forgiving when it comes to noise. Now, some situations, they are going to be worse for noise because every drive is different and it's based on the capacitors and the technology and everything in it. But for the most part, if you're using a Siemens Drive, you can kind of get away with more. But this is how a drive actually creates a signal that is various frequency, okay? So, 101, that's a VFD. And again, if y'all are in chat and you have questions, feel free to just hit me up, and we're going to kind of move into the next little discussion about I want to look at one thing though. Maybe I'm not going to look at one thing. But we are about an hour in and about a third of the way through the material. So this might be a long live stream. So if you're on live, hit that thumbs up and get it out there, because we still got a lot more material to cover, and maybe we can bring some more people into the community. And again, if you are new to this community, welcome. We've try to do a lot of content that helps you out just across your automation growth, and got a lot of different stuff. A lot of it's to do with Siemens, but some of it is other manufacturers, some of it is just kind of general topics. But I feel like you can learn a lot from this channel, even if you're not using Siemens. But if that's something that you'd like to do, please hit that subscribe button so that you can join and get updated with all these, and maybe join in if you're watching this on demand. Yeah, we try to do these every week, try to spread out the times, because we are an international crowd here, because Siemens is the world's largest manufacturer of automation equipment. And don't tell Alan Bradley. But yeah, so we are going to now talk about a couple of different things that happen specifically with drives, and these are going to be what we call control modes. Okay, now you may be familiar with the concept of a control concept. So what's it called? A motor control, or kind of like, what's another way of saying it? Like, I took a class in college that was called controls, and you end up modeling your mechanical system, and then you have this equation for being able to close the loop, and you have all these terms and stuff like that. Basically, what we're going to talk about in terms of the VFD is, how do we control the speed of a motor? Because otherwise, if we didn't care about controlling the speed of the motor, then we would just put it on a starter. we would just throw it across the line and let it run, right? Otherwise, why do we need a variable frequency or a variable speed device? So in VFDs, we're going to talk about, there's 4 major control modes. We're going to talk mostly about 2 of them because they are on the G120, and then we will talk about, well, I guess, yeah, just talk about the other 2 just in passing. So one of the things that when we were talking about how this motor, we need to control the frequency and we need to set the voltage, right? We briefly talked about the fact that we're going to need to set the voltage to whatever that rated voltage is. Okay, well, that's if you were running at the rated frequency. There's a little bit of a concept that is not quite intuitive, but you don't really need to know the reason behind it. But it has something to do with the way the magnetism works in the motor. So it's like a physics conversation. So a motor is like a big complex magnet, and you've got a bunch of magnetic fields like spinning around going crazy. And because of some of the stuff that's going on with that, as you lower your frequency, you have to lower your voltage. Otherwise, you're not able to get as much torque. And there's just it's a magnetization, like the amount of flux starts to saturate, and so you can't get as much torque at that higher voltage. So what all VFDs have to do, what they are controlling at their core, is what's called a volts per hertz curve. And in this, we're going to talk about volts per hertz curve, okay? And this frequency here is the rotor. So I guess not really rotor. It's more, let's call it our what our set point is, because there's always going to be slip. And so let's do it this way, because this is more precise. We always want to be precise with our language. And because in an asynchronous motor, your frequency is actually going to be a little bit higher than what the math says, like the perfect math, because you're always going to have that little slip, remember? And so that's going to be maybe 10, 20 RPM. It's going to be some percentage. Well, no matter what, if we have a set point that we are trying to run at on our US motor, 60 hertz, we want, because that motor is rated at 60 hertz, we want that to be our 480 volts, right? That's what it's rated at. So we want this to hit this point. So 480, 60 hertz. If we were going across the line, that'd be the only option. And then we'd have that, like, that elbow, that knee looking curve. Well, as we speed up and change our frequency, remember, in order to avoid that magnetic saturation that we're talking about, we have to lower our voltage. And it's actually pretty linear, okay? And in a perfect world with no magnetic resistance, again, the physics behind all of this stuff kind of is like, you don't really need to know it. It just, if you want to know, there's plenty of resources out there that talk about the motor portion of it, like the first half of this book. And so, but in general, at 0 hertz, you don't need any voltage. I mean, obviously, if you want to hold some current at 0 hertz, then you're going to need some voltage because there's no energy there. But just in a perfect world, this is going to be a linear volts per hertz curve. So as you speed up, you up your voltage accordingly. So at the halfway point, we would expect this to be 240, right? So at 30 hertz, we would expect this to be 240, and it is. And that's the basic, all in order to control a asynchronous motor, an AC motor at all, you have to be controlling the voltage and frequency. Now, we talked about the fact that you can run faster than 60 hertz. You can run 70, 87.5 hertz, 100 hertz, whatever. What happens though is you can't get any more voltage, right? In essence, and your windings aren't rated for any more voltage anyway. And so what happens is you can go up, but your torque or your power is the same. And so because your power is the same, you're running faster, so your torque has to go down. So like if you were to actually look at the torque would be kind of the opposite of this. I'll kind of draw it over here. Like if this was a torque curve, it would look something like this. And so it's kind of an exponential as you go up. And at some point, there's basically not enough torque to work. And now, the way this looks is all depending on the design of your motor. But this is a control mode, and this actually is the basic control mode. You'll hear it called volts per hertz, or in Siemens land is U per F. And in it, your set point is a frequency, and you say, hey, I want to run at 1700 RPM, and you say, okay, well, this motor has a rated slip of however many RPM, so that means that is going to be a 57 hertz, whatever it is. And so what the drive outputs is your set point of 57 hertz, and then it goes up and finds what voltage it needs to be putting. 460, whatever it is. I don't know. I'm just throwing numbers out there. And it just puts it out there. And in a perfect world, with no load out there, that's what the rotor would spin at. It would spin at 50 or 1700 RPM. Well, the whole point of having this out here is to have a what's it called? A load on it, right? And so whether it be a conveyor or a fan, there's going to be some sort of load. And so your torque is going to go up. And so what will happen is, because it's getting loaded down, you might be outputting 57 hertz, but the torque, remember that torque curve with the little knee? It's going to get its maximum torque pretty low away from the frequency or whatever. And so as long as you're not putting such a load on it that it stalls it, which means it goes all the way and slows down and then it loses the ability to make torque, then it's going to sit, and the rotor might be running, say, at 50 hertz here, but it's still going to be up at this voltage. Okay, so the rotor, because it's loaded down, it's getting slowed down into this like step to where all right, I'm getting slowed down and I can't make it, and this gap here in between the two is what makes the current. Now, as the current goes up, it goes up to 100%. And remember, again, we talked about this in the motor stream, that the rated current is not actually up at that peak. It's actually like halfway down that peak. So you normally have about 200 or 300%, 200 or 300% of a of your rated the current available. So, but that just gives you more torque in order so that you don't stall. Most motor manufacturers will rate their horsepower based on a way to where they try to not get you into trouble. Doesn't mean that you're not going to get into trouble, just means they're trying to help you out. But this is the basic control, volts per hertz. Now, a couple of different parameters that you have on a Siemens G120, for example, is this is what is called a linear torque or volts per hertz curve. This is what's called linear. Well, there's a couple of other things that if you are only using this much torque down here, then this gap at 30 hertz is wasted energy, because you're outputting 240 volts, and you don't need that much voltage for the amount of current that you're outputting. So it would be smarter to, and I say if, there is going to be a I'm gonna change all this. Sorry. I'm using the audio from YouTube, and I'm getting into stuff that actually has lyrics on it for the first time. Sorry. I get distracted by actual, like, lyrics, especially when they're angry. Let me take that off real quick, because we're talking about this volts per hertz curve, and we don't want to. A lot of the big reasons why you would put a drive onto something is you're trying to save energy. If you're going across the line and you're not using that energy, you're just wasting energy by running up at that high frequency when you could be lowering, like running at a lower frequency. And so yeah, the thing about, there are a bunch of different types of loads, specifically pumps and fans, that are not linear loads. Most of the time you're going to be you're not going to be doing like a load that is, the faster you go, the more just straight linear, the more torque it requires. Pumps and fans are what are called parabolic loads, meaning, I'm going to completely clear this out. So we have our volts per hertz like this at their rated frequency. So like at a 60 hertz, most of that, it looks like this. And so if we were to have run a pump on a linear volts per hertz curve, all of this gap here is wasted energy. So if we're running at anything other than 60 hertz, then we're going to be, if we're running down here at like 30 hertz, we're wasting quite a bit of energy because of that frequency problem. So what we'll do is we'll use, instead of a straight linear curve, we'll use a parabolic curve. And that way, that at low speeds, a pump or a fan doesn't actually produce a lot of torque, because the load is a square. And so as it speeds up, the more pressure it's putting on it, and the more it's going to resist, and the more load that's going to get. So we set that frequency, or this would be a parabolic. And there's a couple of other types of options that you get. Like with the G120, there's actually a parameterizable, to where you can actually set at different frequencies what the voltage you want. If for some reason there's some weird resonance or something in your process, you can do that. So, but still, if say for example, you're running at 60 or 57 hertz here, and your your liquid gets colder, so it's going to get more dense. Then, yeah, Jack, sorry. On Mondays, I have to be gone later in the day, and so I can't stream. And so I wanted to get this out here. But yeah, definitely, Jack, catch up. And any of your questions, feel free to drop it in the comments, or yeah, we have a Discord as well. Discord channel is in the comments. You can join up, and yeah. So we're talking about the parameterization options that are available on most drives. The only other one that I would really want to talk about would be what's called the voltage boost. And if you see that your load, you're gonna kind of be operating down here at this point, you notice this is some like really low voltages. Well, you're not gonna be able to produce a lot of torque because of that voltage. And so most of the volts per hertz control will set what's called a voltage boost. And so this might be like 70 volts or something, and it will modify this parabolic to something that's like this. And so it just shifts it up so that at your lower speeds down here, you have that voltage, that extra voltage to overcome friction or whatever, like that's down kind of at the lower speeds. Because lower speeds on a process usually mean higher friction. So that's voltage boost. Okay. And so this is volts per hertz. It is what's called open loop, because you do not actually know if your process is running at the speed that you want it to. You might be sending in a signal to say run 1700 RPM, but there is no way to know whether or not it's running at 1700 RPM. It could be running at any number. Like, even if you're looking at the current, there's no calculation or anything, because you're like, wait a second, there's a math. I did a motor model a second ago, right? We talked about there has to be some math, some calculation based on the voltage, the frequency, or the voltage and the current, and to kind of like back your way into the frequency. And well, if you ask that, you'd be totally right. That is called a vector algorithm. Okay? And the reason it's called a vector and vector control, do this. So a vector control, it looks at, if you're not familiar with these terms, it's fine. In math, you have the vector of a variable is kind of the change, so the velocity. So you create a vector with what you're supposed to have, velocity, not velocity, your voltage, frequency, and current. And so you look at that vector, and then you look at what you are actually experiencing, and then you can infer the difference in vector. And so that's what this calculation is. And it has to have a pretty accurate version of that motor model I kind of scribbled out earlier when I was talking about how the waveform gets smoothed out. Well, that motor model, if you have a pretty good idea about all the variables in those, then you can kind of do some math and calculate the speed, the actual rotor RPM of this motor. So you have a set point, and then you can calculate the actual RPM. Well, the whole point of a closed loop control mode is to be able to eliminate the error. So the error is going to be, and I'm saying in my redneck, ERROR, error. Sorry, I'm from Alabama. I mean, I live in Atlanta, still in the South, but my coal miner redneck makes error. I can't pronounce it. So the error of the signal is like your set point. So like in a PID, what is the difference? Yeah, error. So the error is the difference between what you are actually running and what you are telling it to run. And in a closed loop control mode, you can actually force it. You can say, hey, I'm sending it to run 17 RPM. For some reason, it's only running 1650. So let's change something in order to force it up into 1700 RPM. And your vector control model does this by using that motor model, and it does a math calculation to close the loop. Now, there's another way to close the loop that probably everyone knows about, and it's a little bit of, not a pet peeve of mine, but it's a little bit of a pet peeve of mine when people call vector control open loop, because the reason they say it, and it's because they're like, oh, it's not open loop because there's not an encoder. Well, vector model, the math is the encoder. It's just, it could be off because things change with your motor. So like as the motor heats up, your resistance is going to change. And so that's going to change the model a little bit. And so if you don't have a temperature sensor, then your calculation for your feedback for your speed might actually not be correct. So, all right, I'm going to have to get back to the music again. All right, we're going to do this. We're going to go back to my regular, just electronic. I tried hip hop. This didn't work. So, genre. Here. Let's go and yeah, here we go. So, that vector model is actually bringing in and creating kind of like a math version of an encoder to close the loop. So vector control is closed loop control. It just uses math. And what it is doing and the way it kind of works is, go here and do this, is it sits and it outputs just the same. It uses that same volts per hertz curve, except it doesn't really care about necessarily the kind of like what you were outputting in terms of frequency. You are actually outputting a speed, so a motor RPM, so a rotor RPM. And so if 57 hertz is supposed to be 1700 RPM, then that's going to be your set point. And what it'll do is it'll sit there and see, all right, it'll be outputting the correct amount of voltage based on your volts per hertz curve. And it'll say, okay, based on what I know, I should be outputting this much current. Well, if it's running slower, then it knows that, hey, I'm not actually, sorry, if it's running slower, that the current's going to be up. And so it's like, hey, this current's wrong. So what do I need to do in order to make the rotor, because I see that you want it to run 1700 RPM. It is actually running 1650 RPM. So what should it do? Well, it says, all right, there's a load there that's not in my calculation. So I'm just going to up the frequency until I actually get a 1700 RPM speed. And so while in theory this is saying it's outputting 57 hertz is 1700 RPM, because of the load, it's going to go through and it might up that to 59 or even 59.5, 60, whatever it needs to actually output in order to move that up to 1700 RPM. It's going to do it depending on what the load is. And so that's what the vector control model does. It goes in and uses the kind of like general concept of volts per hertz and just bumps it up. Now, I want to talk real quick about something that may happen, because we've been sitting here and talking about a load that kind of slows down the rotor. Well, what if you had a load that actually speeds up the rotor? And that is a concept called a generating load. And an easy one to think about it is if you have an elevator that's neutrally balanced and it goes up to the top floor of a building, and somebody loads a bunch of people onto that top floor. Now it's heavy, and so it's wanting to fall. And so if you were to just let it go, you would start singing a Disney movie. But if you just like let it fall, it would start to accelerate. And so the rotor would start to speed up. And so that would actually be what's called a generating load. And so the load is causing the rotor to speed up. A motoring load is one where the motor has to input energy into the system in order to speed up. So what happens in a generating load? Well, obviously we need to break it, right? We don't want those people to fall to a CNN article at the bottom. Like, we don't want that. So what happens is the same thing. Say it's wanting to run at 800 RPM. So that would be around 30 hertz 900 RPM. That would be around 30 hertz for a US system. So say it's wanting to run 30 hertz. And it does the calculation and it says, okay, I'm outputting 30 hertz. What is it actually running? Well, it's running up here at, say, 35 hertz. Okay, well, obviously it doesn't want to speed up more, so it wants to pull that down, right? So it would actually start to lower the frequency. So the rotor is always going to generate torque to match the line frequency. And we didn't really talk about it in this stream very much, but in that, we'll clear this, in this kind of motor curve that we talked about that kind of look like this. Well, this is the base frequency. And so if we set our line frequency to 30 hertz and it's running out here at 35, it's actually going to be generating negative torque like this. So it says, oh, I'm generating negative torque. Well, negative torque is negative current. So that the sign on that is going back into the drive. It's not going out to the motor, it's going into the drive. And so we'll talk about just briefly, well, I guess right now, the drive has to be able to handle that sort of situation. On a G120, you do have a regenerative option to where you can put that back on the line. But most people on general purpose drives, this is not a very common situation. So what this would normally be is if I'm trying to slow down a motor, right? You're pushing this frequency, you're shooting it down. Well, obviously the rotor is not going to be able to act instantly, and so you create this gap and it creates this negative torque. That's braking torque, and that motor or that current is going to go back into the drive because now your motor is acting like a generator. So there's two ways to deal with this. One, you can not brake as fast because there's a little bit of resistance in those capacitors. If you keep filling them up, they'll just explode. So you can't just pump infinite energy into those capacitors in the DC link. So you have to get that energy out somewhere. All drives have some internal resistance that they'll be able to take in a little bit of braking power. Drives are different. Some drives have more built-in resistance, some drives have less. I'm not here to talk about like specific drive manufacturers, because I in general only know a lot about Siemens. Most people will put a braking resistor on the bus, and what it will do is it will chop out that voltage and break out all of that energy out as heat into a big braking resistor. And so that's called active braking, or regenerative braking. And so there's two situations where this happens. In when you're slowing down, so if you slow down really fast, you have inertia, and that inertia is going to want to keep going, and you're slowing this frequency down. And so you're doing this to where essentially you're shifting. This is the rotor speed, and you're shifting the curve further and further away. And so you're making this gap, right? That's what you're doing. And so that's braking. And so when you're slowing down, you will need to brake. That's active braking. You either need to have a regenerative drive or a braking resistor. Otherwise, well, I guess there's another option. So you can either have ways to get that energy out of the drive, or you can just say, hey, if that DC link voltage gets too high for those capacitors, how about let's have a system that automatically kind of slows down a little slower. So like instead of like slamming on the brakes, it kind of eases off the brakes. Well, in some cases that wouldn't be a good thing, but in most cases, if your load takes a quarter of a second longer to brake instead of blowing up your drive, that's probably going to be a good thing, right? Especially if it's like a pump or a fan or something like that. And so that is called the VDC Max controller. All right, and this is in Siemens, and I don't know what the other terms, but most drives have this. And essentially what it does is it takes and lowers the deceleration in real time just to keep your drive from blowing up. Now, how fast that reacts, how fast your load is, that's based on the manufacturer. So that's braking. Anytime you slow down or your load tries to push up against the motor, you're going to have to take that energy and put it somewhere. And a lot of people will just dump that energy into a braking resistor, and they put the resistor up on top of the panel, and it heats up the room, and it's a nice little warmer heater in the winter. But you're just wasting that energy. There are a couple of other ways that you can do that. You can either do regen, like we talked about, or use common DC bus, to where if you have one that energy is going into the DC link. Well, if you have multiple inverters sharing that DC link, then a load that's motoring and a load that's generating, that generating load just shoots that energy over, and the motoring load just sucks it up. And then you just have less coming back from the line, which, by the way, is why the common DC bus lineup, like in the S120 on a lot of other streams, that's why that is such a good setup, is because overall, if you have a load that's going to like cause this sort of issue to where you're generating, motoring loads can immediately just use it, and you don't have to like send it back to the line. All right, the last control mode that we're going to talk about, which, by the way, VDC Max, you probably want to turn that controller on unless you have a really good like active line module system. Probably want to turn that on just in case, because again, most applications, it's better to run for a quarter of a second, half a second longer than blow up the drive. Because if you blow up the drive, it's not going to slow down any faster anyway. So yeah, that's something that normally you never turn off. And on Siemens drives, by default, it is turned on just for that case. So let's clear this out and talk about the last version, servo control. So if you're just now joining, or you're joining in on demand, welcome to the stream. I always try to give these plugs. If you haven't already, check to make sure if you're subscribed, if this is some content that you would like to see. I do these live streams I try to do them about every week. Sometimes it turns into every 10 days or so, because I do have my own automation company that I have to run as well. Or I get to run. I actually love doing this, so I'm kind of like retired. But yeah, be sure to hit that subscribe if you haven't, and if you're on the stream live or you like it, please go ahead and like the stream to get it out there. The YouTube algorithm really loves people subscribing to stuff, people commenting, people liking the stream. Loves it to get out there and just continue to grow this community, get all this information out there. So appreciate it. So we're talking about servo control, and most people, rightfully so, think that servo control is only for one of these guys, right? And so they call these servo motors, right? Because you do have to use servo control. So this is a permanent magnet synchronous induction motor. Okay, so on the rotor of this thing is a bunch of magnets instead of an induction motor. This is a synchronous permanent magnet motor. To run these, you have to have an encoder. You have to run these in servo control. You cannot run these in vector mode. Just the math isn't there because there's no vector to be able to calculate. So what servo mode is direct control of the feedback is directly generated by the encoder. So this on the back here, this little green cable, is the encoder. And it says, hey, the position of this rotor is this. In one way or another, it could be incremental, it could be a resolver, it could be absolute, it could be absolute multi-turn, it could be all sorts of different types of encoders. But the signal that comes back is, here is where this rotor is. Which, by the way, this little gear looking thing, check out the Design and Chill if you're interested in this. This is a part of a Delta picker that we are building and designing live on stream. So if that's something that might interest you, and 3D printed back behind this, definitely not fake wall. But yeah, that interests you, check out those streams, and we'll probably be having one of those Design and Chill streams tomorrow, because I like doing this sort of stuff, and it's hard for me not to just design for a little while. But back to the motor. As this spins, this encoder tells the system where this is actually aligned. And so that's very important for these, because otherwise it wouldn't know where the magnetic field is. And so it would have no way to really generate and do the control. Now, so the reason I say that most people call these servo motors is because they do require servo control. And that's perfectly fine. It's a little bit confusing though, because most people think that for an induction motor, you use vector control, and for a servo motor, you use servo control, right? Well, I'm here to tell you, you can actually use servo control on an induction motor, because all servo control is instead of using a calculation, you use a piece of equipment, and you get the feedback instead of from a calculation, you get it from an actual piece of equipment. Now, there is what's called closed loop, or not sensorless, but a speed control, vector control with encoder. But what that is doing is it's taking the speed value from the encoder, doing the calculation at the same time, and then combining them, and just say, or looking at them and kind of like checking and like saying, all right, that's good. I don't have anything crazy. And the reason you would do that is just an induction motor does do a little bit better in some ways that, like in some applications, if you were using vector control. Just because if it's calculating all those things, it can kind of better predict what's going to happen. Whereas servo control, it's just sitting there and saying, hey, here's how fast you're going. I have no idea how fast you're about to be going, but yeah, here's how fast you're going now. But, so, all it is doing is, in our little diagram here, we have our controller and our motor, and then we'll have some sort of feedback, and it's coming back in, and it's giving, in here, it's giving the actual feedback, okay? And then the output is going to our motor. And we're not going to really go deep into what's going on here inside these. Just know that servo control just means you are only looking at an encoder. So you can absolutely, we have actually a roofing line in Alabama that is running in Blackmax induction motors, and Lucid, no, it's not yours. I don't know, it actually might be yours. But we are running Blackmax induction motors in servo control mode, and it's just straight servo control. And the reason we do that is because of some features and stuff that we get in technology objects, and that don't really matter right now, because yeah, just know that you can run an induction motor in servo control. You get tighter speed control, but usually you're kind of giving up on torque, like the torque kind of like fluctuations, just because the speed is being regulated so tightly, because that's all it's really looking at. And so you can get into situations where your torque can see fluctuations and if that's a problem, then it might be a problem, obviously. So that's what we have here. That's servo control. And those are your three main methods of control for an AC motor. The last control method is what's called torque control. And I will be honest with you, there are very few applications that I would suggest using what's called pure torque control. Torque control is, let's clear this. It takes your controller. There's no speed loop. There's no volts per hertz. There's no nothing. It is just, well, there is a volts per hertz. It's outputting a frequency, and then it is only outputting the current. And so, like, whatever the motor does with that, it is just outputting torque. And so it's creating a torque in the motor, and it's not regulating speed at all. And that should, when I say that should kind of cue into your brain, wait a second, you're not trying to control the speed at all on your variable speed drive. What in the world? Why would you do that? Well, I mean, there are applications like winders and unwinders that people may want to use it. But one of the things is, if you don't have any sort of speed regulation and you are outputting just a torque, you say, hey, I want to put this motor to produce 10 Newton meters of torque. Well, it does whatever it needs to in order to control and create 10 Newton meters of torque. Well, what happens if you don't have a load? Well, in an instance where maybe a coupling breaks or a shaft on breaks, all of a sudden your motor doesn't have that resistance, that load, and it's trying to say your torque set point is set to 100 Newton meters, and running the motor at any speed only ever produces 50. Well, it's trying to do whatever it can to get up to 100 Newton meters. Well, it's called a runaway, and there's plenty of songs, American songs, about Janie being a runaway. but you don't want your motor to run away. And torque control inherently poses the risk of a mechanical breakage causing the motor to take off. And there's some very few applications that might be needed, but I talk about a much better way of controlling a motor if you are needing that tension control. I have 2 different live streams that talk about a much better way of replacement of using torque control. And those are the load sharing live stream and designing a winder live stream. And in both of those, we talk about how to create what is called a speed saturated torque limited setup. And in that setup, you are still using speed control, so either vector or servo control, but then you are controlling the torque directly in the same way that you would with a torque control mode. But if something breaks, it can only speed up, and it'll make that speed limited move. And so you'll only essentially overspeed by a few RPM instead of a few thousand RPM and destroy your motor. So all that said, there's technically 4. There's volts per hertz, there's vector, there's servo, and then there's torque control. Volts per hertz, open loop. You don't really know what the speed is, but it's great for pumps and fans and things to where you have like, you're running a PID controller off of like pressure. You don't really care about what speed it is. You're going to be changing that frequency set point anyway based off of pressure. So volts per hertz works really great for those type applications. Vector control, great for like conveyors, things that are going to have some sort of load on them and you want them to kind of run all the time. That's really good for those type applications where it's based on speed, because vector control is closed loop even when you're not using an encoder. And then servo control only uses an encoder. It doesn't have a calculation that's involved like with the vector control. Servo control is only an encoder. And torque control, don't consider it unless it's absolutely you know what you're doing, because you're asking to get fired. That's just my opinion, and I hold to my opinion. So let's go through and kind of shift gears. We are running into almost hour 3 of this live stream. And so let's go through and actually go through the kind of talking about Portal and how to actually control a G120 drive. And this is kind of like for ProfiNet, a little bit about the communication, a little bit about the telegrams, a little bit about how to make the PLC data types to control them. And so what we're going to do here for the next, hopefully, less than an hour or so, we're going to go through and set up a G120 and go through and kind of step through the way to control it via just a custom PLC tag, so you really understand kind of what's going on with everything that's there. So we're going to make a new project, and I'm going to move this back a little bit. We're going to make a new project, and we're going to call it Drives 101 Live. And again, as we're getting through this is kind of getting into the very Siemens specific. Everything up to this point has been manufacturer, not necessarily manufacturer specific. But I want to talk to you just a little bit once we kind of get this going. I'm going to kind of blow through this. There is an introductory class on how to actually set all these things up. You could check that either live streams or here, I'll use my standard. Well, we'll do this one with a 1200 just because it doesn't really matter on this, because we're going to be using we're going to be using ProfiNet, and ProfiNet's really processor, like, it's not really intensive on processor. Just using the way that we're doing it is a very standard and kind of like, no matter what type of PLC you have, you're going to be able to do this method. And so we're just going to bring in a PLC, and now we're going to bring in just a G120. And you'll notice on this that the first thing that comes in is the control unit. And so you just pick your control unit, and for this we're going to use the we're going to use the 240E-2PN because we want to use ProfiNet. And we're going to rename it. And we're going to assign this to that PLC, and it'll make that connection. We're not really worrying about the addresses on this, because what we're doing is I'm just going to go through and kind of talk and show you how to kind of set a couple of different control modes and things. And we're going to go for this. I want to go to the drive. I think it's here. Maybe not. So just checking to make sure all of these are the same. Oh yeah, that's right. I remember. And so now we're just going to put in a power unit. On the S120, you can actually select your control mode on that screen. Let's just bring in like a 7.5 kW, since we have a few of these sitting in our shop. Okay. So, and then now what we have is a PLC that on our network view, PLC is connected to a drive, and if we go, if we double click there, and yeah, so let's go back to the PLC now. Actually, no, it's not. It's here. We're going to click here, and then we're going to go to Telegram configuration. So Telegram configuration is the way that we actually go through and communicate to the drive. And if you're not familiar with kind of setting up protocols are just bits, bytes, words, like sections of data that are sent and exchanged back and forth between the PLC and the drive. Well, in this case, we're going to use a setup telegram, in this case 352. 352 is a really good telegram if you're using a Siemens Drive, because it gives you current feedback, and it gives you the ability to be able to do that saturated speed controller that we talked about before. So what we are now going to do is I'm going to show you. So this drive here is a 66 words, okay? And what we want to do is go in and show that this is from the PLC perspective. Actually, so this is from the drive perspective. These inputs and output address areas are going to be on the PLC where the data is going to be coming in. And here in a second, we're going to just go through and build what's called a PLC data type that describes how to control this drive. First thing we need to do is figure out the control word for this. Now, there is a couple of different blocks that you can download and use, and you can see the SINAMICS Sina speed can actually use this, because the control word is the same as the 352. But we're going to go through now and we have essentially set up this drive, the PLC and the drive, to be able to communicate back and forth. Now, we're not sending any data back and forth, but if we were online, we could go and do a download to this PLC, and then we could click here and then do a download to the G120, and it would download all the setup and configuration, and then we could do some things online in order to like do the motor nameplate data and stuff like that. But to set up the communication, this is all we do. Pick the Telegram type, make sure that on your network view, you have this little, that the drive itself has the PLC name under this. If it doesn't, if it says not assigned, just click on it and then select the drive. And so yeah, so when you download to both of these, you should get red light communicate, or all green lights on the communication. If you don't, you may need to do a power cycle. One thing about these drives, if you're not familiar with them, is that when you do a download, you'll get an option to copy RAM to ROM. The first time, you kind of always want to do a copy RAM to ROM because you've done a bunch of stuff offline, you want it to stick, and especially when you're setting up communication, sometimes you've got a power cycle, and if you don't copy RAM to ROM, when you power cycle, you'll have a default drive, and you'll have to do all of it over again. So copying RAM to ROM saves the drive state to where when it's powered up, that's what's going to be there when it's powered back up. So we are now going to go through and try and figure out how to actually control this thing. So we're going to go to the parameters of the drive, and there's kind of, I guess, the best way to go through because we don't have any motor data set up. We have this commissioning wizard that we can go through, and here's kind of the way that you could get standard drive control is going to be volts per hertz. Dynamic drive control is going to be vector control, so precise vector control. And standard drive control is going to be your volts per hertz. But we're going to go right now and just click on expert. And so all setting options of the wizard are available. I normally do that because, I mean, I'm used to seeing all the options. So a couple things, the ramp function in the drive is normally what you would want to do. That would make the parameter, that would make the parameters to where you can set a, like, from 0 to 100%, you would set, if you wanted that ramp to be 10 seconds, you would set it to be 10, and it would just do it. And so you could change a set point immediately, and you don't have to worry about ramping up the set point. You can just send it 1,000 RPM, and then it'll ramp up and it won't fault out. That's what this is. So I recommend that. And so on the control type, so I want to go through and set this up for speed control in coderless. Okay, and again, this is closed loop because, as you notice, this is kind of your set point channel. It is closing the loop in your set point. If we click over on volts per hertz, it is open loop. There is no loop here. It is open loop. And so just, we kind of talked about the different volts per hertz control methods. Here's your parabolic. Here's your parameterizable. And then there's some other stuff here that, I mean, could be something that you talk about. Most of the time, it's either going to be linear or parabolic. So linear would be like a conveyor that you don't really care about the speed, or in parabolic, you would want to be like a pump or a fan. But we're going to do speed control in coderless because the CU240E-2 does not have encoder feedback. If you wanted an encoder feedback on a G120, you would need to get the CU250S-2. That gives you encoder feedback. But so we're gonna go next, and we've already selected Telegram 352 because we want that current information coming back. And you can see this is digital inputs and outputs, and this is how it's set up, like the actual configuration on the front panel. I'm going to change this to NEMA, and that should change up to 480. And our load duty cycle, we want high overload. I normally rate mine on high overload. Again, if you don't know, if you're not familiar with those terminology, did a whole video about a live stream about sizing industrial motors and drives. I think it's about 2 or 3 weeks ago. So check that live stream. I'll show you how to set up a braking resistor, but I'm going to uncheck this. So maximum braking power, however much power you can put out. Say it's this is the maximum continuous amount that you want out. Now, braking resistors are kind of funny. If you're using a braking resistor to brake and you put this value in, and it's just parameter, does it show it on here? Yeah, parameter 219 is braking resistor power. If you have a, say, a 7.5 kW peak resistor, and you put 7.5 kW or 10 horsepower in here, and you're basically always generating, you're going to burn up that resistor. So they have a continuous load and a peak load, and most of the time, who knows, like the manufacturer, depends on what they actually do. So this is a continuous rating, and you can play with your ratings based on the duty cycle. Don't think that you have to put that continuous rating in this box. If you're only braking like 20 seconds out of 2 hours, then sure, you'll be able to like handle that duty cycle. So, but yeah, so that's the braking resistor. That's all you have to do to configure it, is literally change P219 and put a value in P219, and it will start chopping. If there's not a braking resistor there and you have a value in P219, then it will fault out on open circuit in your braking resistor. It'll be like a 30,000 fault. So be sure on that. So we're going to disable that. And motor configuration, we're going to enter motor data, and we're just going to do an induction motor. And I'm going to, here's your star connection. We're going to do like 460, do 12 amps, 10 horsepower, efficiency. That's a pretty small motor, so let's just do 90%, 60 hertz. Rated motor speed, this is probably going to be about like 1785, something like that. And we put all that in, and we go from there. And when I clicked enter there, it did a calculation behind it and made sure everything made sense. One of the things that we talked about with a motor holding brake, these drives do have holding brake control, and you can select it here, and the brake opening time and the brake closing time are big deals. By default, they are 100 milliseconds. That's a very small brake might be able to handle that, but if you have some sort of application to where you need that brake to be engaged before you let off torque, then you need to set this brake closing time in order for it to actually, what that'll do is it'll hold 0 speed and then wait this amount of time before saying, okay, I'm going to power down my motor. So if you have a significant brake that actually is like a drum brake that you're controlling with this, you need to set this for like 1.5 seconds, 2 seconds or something, to make sure it gets all the way down, and then goes, and then it releases the torque. Because otherwise you might get in a situation to where the brake is coming down, the torque drops off, and then it starts spinning, and you prematurely wear out your brake because it's slipping. So because it's spinning, and then you're stopping it physically with those brake pads. That's if it'll stop. Most holding brakes aren't actually rated for stopping an inertia. And so they will eventually really quickly wear out. So that's what these are. They're parameter 1217 and 1216. So if you don't get to this page, then you can still always go to the parameter list 1216, 1217 and set these up. Now, these reference speeds here are very important, okay? By default, the reference speed is 1500 RPM. And the reason why these are very important is because we're going to talk about how our communications scale. Everything in the drive that is a value like amps, voltage, hertz, speed, these are all based off of these reference parameters. Well, this reference speed for a what's it called? A 50 hertz 50 hertz motor, this would be fine. 100% speed of a 50 hertz motor would be 1500 RPM. But we have a 60 hertz motor. We're in the US. So we're going to change this to 1800 and we're going to up our maximum speed to 2000. Now, if that's not what your motor is rated, you probably don't want to do that. And I'm going to show you how that changes, because in the US, we would want like a 1750 RPM, 1800 RPM frequency, right? That's the speed that we would want at 100%. Maybe we put this at 1785, like our actual rated, but for right now, we'll just do 1800, because if we don't do this, then all of our numbers will be based off of 100% being 1500 RPM. Well, what if we want to run 1700 RPM? Well, then we have to input over 100%. So that's just based on a 60 hertz system. We need to set this, and I'm going to talk about that more in depth here in a second. Current limit, by default, it's going to be 1.5 times. 1.5 times your whatever value you set for the motor rated. Now, you can mess with those values, the nameplate ratings, to change these internal volts per hertz curves. But right now, we're doing standard ratings, standard stuff. Standard current limit, that's 1.5 times. That gives you your overload rating. And here you can set your ramp. We're gonna set this for 5 seconds. And you always want your off one ramp down time to be something that you hope can actually achieve. We don't have a brake on this, or a braking resistor, so we will probably set it to be a little slower than our ramp up time, okay? Just to make sure that we're not activating that VDC controller. So technology object or technology application normally is a standard drive. If you're doing a pump and fan, you can put on that. Normally though, I would just leave it as standard drive. And we're always going to want to do a motor data at standstill the first time, because it will actually go out. And so we're going to do this complete calculation of the motor parameters. It estimates our motor model, and then that identify motor at standstill, the first time we turn the drive on, it's going to do, some people call it a wake and shake, but you just hear it pulse, 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 and it actually measures most of those values that are calculated here, and then it makes your motor run a lot better. So we're going to finish this, and that's really setting up the bulk of our motor. And so we're going to clear out of this. Now I will say, in a real situation, at this point, you would probably go to your control panel. You would activate, you would set your drive enables, you would turn your thing on here, and then you would just run it forward, and it would do that motor optimization. Then you would want to go straight down to backup or restore and click save. That's copying RAM to ROM, and that'll just save your motor ID data, because if you don't do that, every time that you have a power cycle, you will have the motor ID on, and you will have to start it. It'll go through the motor ID, and then you start it again. and it'll actually run. So remember that. Control panel, run the motor ID, and then copy RAM to ROM. And then we're good on this. So now I wanted to show you, I want to go to the communication, and because I want to go through and set up our transmit, our PLC telegrams, okay? And I want to show you, we have a Profi Drive. Don't worry about the Profi Safe right now because we're not using safety. So we're going to look at what our STW, so this again is from the perspective of the drive. This is what the drive is receiving from the PLC. So that's what it says, receive direction. And the first word is 16 bits of control bits. And we're gonna set up a PLC data type to actually interface into these. And it's not quite as straightforward as you might think, but it's still not too bad. So, and then what's receiving from the PLC is main set point. It's connected into parameter 1070 by default. When you select the telegram type, it automatically sets these parameters. And then you have 4 words of what's called user data. So some of the blocks that you might see out there will have some inputs that'll be like PZD123 user or something like that. And it can get a little bit confusing, but these are just custom things that you can freely tie into your drive. Now, I personally on all of my drives that we do at Alpha, I set this to be a upper torque limit and then this to be a lower torque limit so that we could do that speed saturated torque limited setup that I talked about before. But we're not quite going to do that this time. Check out those other streams if that's something you're interested in. Show very much how to set up the interconnections in the drives. I show those on there. So now we want to look at the transmit direction. So this is the drive transmitting out to the PLC. That's what's going on now. And again, Profi Safe is something we're not using. It is selected 352 telegram. And it has a status word. And we're going to click on it. And here's the status. And we're going to go through and we're going to set up a lot of these. Some of these we won't necessarily need, but we definitely want that alarm present, fault present, that sort of stuff, right? Maybe this in actual is greater than or equal to 0, so it's actually running. Maybe we want like this operation enabled because that's important. So we'll go through and set these up here in a second. I'll show you how. But if you notice, what it's sending back to us has a lot more in it. Okay, and so we have our actual speed, which is standard. We have our absolute current. Then we have our torque actual, and those are two different things. It's a little bit different because absolute current just means physically how much current is going through the motor, and then the torque is actually how much torque that motor is producing at that given moment. And those aren't always exactly the same. And then we have our warning and fault codes. A little bit about these drives. A warning usually will not shut the drive down, but you can absolutely program your drive to shut down on a warning. And a lot of OEMs will do this for some reason. Maybe they don't quite understand the difference between alarm and fault. And so they will take in our status word here and look at this fault present and this alarm present, and they'll take both of those bits and say, hey, if this drive is in this, shut the process down. Well, a warning does not actually stop the drive. It doesn't fault the drive out. And so if you do a warning that way, you may be shutting down your process for no reason. But normally those warnings are like, hey, this motor's getting hot. hey, you're in current limit, stuff like that. And while those are perfectly fine, like you can keep running, you probably need to like look at why that is if it's unexpected. Now, like if you're in a current limited torque controlled sort of thing, like that sort of setup, you're always going to be in current limit. So you actually most of the time disable that warning. So what we're going to do now is we're going to go into the PLC drive and we're going to create these tags, because all you need to do in order to control these drives, you don't need a fancy block, you don't need all of that. You just need 2 tags that are pointed to the addresses that I showed you earlier in that Telegram configuration. And you can go through and make it easy like we're going to do, or you can just kind of like the way we would call it, like you could just bit bang it and like turn on individual bits, and like for like random bits in a tag or in a word, you can absolutely go through and just say like address a bit, and you know that it's this bit, and then turn it on and no tag involved. You can do that if you want to. You can do that if you hate yourself or the people that are working on it behind you. But what we are going to do, we are going to create our data type, and we are going to call this our drive 101 352 tel in. Okay, and then the first thing that we're going to do, and then, well, we'll do this as well. I'm going to do drive 101 underscore 352 tel out. Now, those are from the PLC perspective, okay? So those are PLC data tags. So what's coming in is going to be the receive direction from the drive. What's going out is going to be tied to the outputs, and so it's going to be the sorry, I said that backwards. What's coming in is going to be the transmit from the drive, and what is going out is going to be received by the drive. So let's take and let's look at the tel in, which is going to be the parameters for transmit. And first thing we have is 16 bits. Okay, so let's go ahead and set that up. Tel in. Let's set up bit 0. It's a boolean, and do that. And I'm doing this for a reason, because you have 2 separate bytes here. And unfortunately, what happens in what we see here gets what's called byte swapped. And so 0 here, this 0 is actually 0 of the first. So we'll do ready for switching on, and I can't select that, which is kind of annoying. So we'll do this. So it's not here, it's this 0. So like this. And I have a hard stop in at 1 that I have to jump off of, so hopefully we would be able to get all of this done. But I'm gonna go through and do the ones that you actually would probably need. So this is operation enabled is going to be .2, because a lot of these are redundant, and so like here's this thing like speed set point, actual value deviation intolerance T off. Like that is actually pretty important. That's going to be like, hey, my set point reached bit. And so let's do this. Let's go and do a .2 is going to be operation enabled, .3 is fault present. Now here, there's two ways to kind of do these. Like, if this is a common status word, which it kind of is, we might actually want to set this up as a separate subtype, and just change the data type of our tel in. But for this one, we're doing everything in one telegram in, just so I can show you the easiest way to set these things up. So if you watch some other streams that I do this, I do it a little bit different. I actually, instead of just having 2 data types, I'll have 4. I'll have a status word and a control word, and then my tel in and tel outs. And the first value in each of them will be those status and control words. But we're just going to do it all in one. So fault present, click back here. Let's see. You want this one, this .6. So switching on inhibited, because that's something that's important. So .6 and 7 alarm present. And obviously you want this fault present and alarm present. You want to be available to you for like your HMI diagnostics, things like that. Obviously, these bits are going to be here and they will be active. They're just not named right now. And so you could go in and fill in anything that you wanted. Let's see, is there anything else that we wanted here? I think, yeah, we said we wanted this .7, right? Or not .7, this .8. So this 8 is going to be 0 of the first. So we definitely want that, and that's going to be set point reached is what we would call. So let's do 0, set point reached. And I think everything else is yeah, I think that's good. So 0 is going to be set point reached. Now, there might be one that you might want to use this, the thing's actually in motion. So bit 14, so that's going to be bit 6. Okay, so there's our tel in. We're going to save that for now. Let's do our tel out. So this is going to be our control word. Well, actually, that's not our tel in. I lied. So let's go back and look at, so this is our actual speed, current, torque, right? So it is an integer, but we're going to talk about the special natures of this. And this was checking time. This was alarm, right? Click on the right thing. Yep, warning. Warning, fault. And we want to change these to unsigned because they are positive. Okay. So now that is our tel in. So you go 1, 2, 3, 4, 5, 6. That's good there. And then now let's do our tel out. And this one is going to be, we're going to do it the same way. So bit 0. We're going to do 7 of those. Bits 1 underscore 0. now let's go to receive direction and check out the status word here. Now, there's going to be some of these that we're going to talk about. This bit 10 here, if you do not have that turned on, the drive will not accept any communication, and it won't even update these little bits and the symbols in the table. If it does not have, like, if I were online and the drive was running, these little lights would be green and like whatever is there. If that bit 10 light is not green, nothing is being updated on this screen. So that is the first thing that we need to do, is figure out what this bit 10 is. And so we look, so we know it's going to be bit 0, 1, 2, right? And so, wrong one, 0, 1, 2. And if you do not turn this bit on, nothing works at all, ever. So, and this is a big thing, because if you were to go through and be like, oh, it's bit 10, that's this guy right here, right? And you turn that on, it's not going to turn on. And not only is it not going to turn on, it is not even going to update in the drive. So you think that you don't have communication, when in fact you do. So a little word of advice is a way to just, if you want to check how, I guess, if you want to check to make sure you have communication to a drive, it's not going to run the drive. But if you just do a move command to the first address in this guy here, so if you were to do a move hex, so 16 pound FF to Q256, then this, if you have proper communication and you are online with your drive here, this bit, all of these will be on, because an FF just means all bits in those 2 bytes are going to be on, right? So FF turns on all the bytes, so you know that you're going to capture this bit 10. You don't worry about byte swapping, and you know it's going to turn all on. The cool thing about the drive is if you send a FF like that, you're like, I'm going to turn the drive on though, and it's going to start running. No, it won't. You have to, that bit 0, everything else has to be on, and then you have to turn on the on-off one. So if you send them, it rejects the command. So that is a way to do it. Obviously, if you're commissioning and you're just getting stuff going, and you need to have your actual motors and stuff disconnected, like motor disconnects and things, just for safety, just to make sure that something crazy doesn't go on. But you can do that. You can send it FF. All of these bits will turn on, and you can check to make sure that you're communicating. So the next ones that we're actually going to want to toggle are going to be this on-off one, which is 0. So that's going to be that 1, 0. So let's just do this. So we're going to do off 1, off 2, off 3, because that's how those are. And so we're going to start here. We're going to do off 1, off 2, off 3. Now, off 2 and off 3 have to be on before off 1. I just said that. We've got some other stuff that has to be on as well. And honestly, you can go through and set all of these to a 1 in the drive itself. So you can kind of like disable those communications, but you cannot do that with an off 1, because it has to cycle. It can't be at the same time as all the others. So let's see, 3, 4, 5, and 6, we all have to be on. So we can, so enable operation, ramp, continue, set point. And those are kind of annoying that And what these are just inside the drive. There's all these bits that control different set points and different control parameters and things. And the enable operation is kind of, yeah, I'm not, at some point they had it, and these are kind of like, I guess there's a particular reason, but this enables the actual bridge. The enable ramp function enables the ramp function, like that set point path. If this is not on and you're using the ramp function, you have it set up to use it, you're not going to get your set point's going to go from whatever it is, it's going to go to 0. So it'll be operation enabled, and then you're not going to move. Same thing with enable ramp, continue ramp, and set point enable. There's all sorts of different reasons why you might want to do that. None of them we will talk about. So essentially what we're going to do is these first, these from bit 2 to 6 in this, we're going to turn on, and for the most part, just keep on. We'll actually tie them all together in logic. And so now the only other, let's take one last look. I don't think we need anything else. Oh, acknowledge faults is bit 7. So let's put that. Yeah, so if you want to reverse without doing like a negative set point, you might have to do that. So we'll just put that in there. So that's here. And there might be a reason you'd want to do that. There is a bit, like when you go through, or a value that sets the rotation of the motor, and so it kind of like changes the firing order of the pulses. And so when you're initially setting it up, you wouldn't want to use this reverse command, because for some reason it might go off. Just set the drive up to where it's turning in the correct direction first, and then if you want to use this reverse direction, all it's doing is throwing a negative into the set point channel. And so you can do the same thing by sending it a negative set point, which we'll talk about here in a second. So let's do the last things on this. So we just have a main set point, and it is going to be an integer. We have and it is an int. And honestly, we don't have anything else coming back right now. So this is all user data. So we actually have 4 more words that's like user. So we could do like user 1, and then like this right here. And so there's a couple of blocks, like there's a SINA 352 block, and it has these like user 1 through 4 things in it, but it doesn't quite make sense because it talks about this being, I think, PZD 4 or something like that, 4, 5, 6, or sorry, 3, 4, 5, 6, when it's really, yeah, that's what this is. So that data can come back. We can tie some stuff in the drive to that to send it back. But now all we have to do, now that we have these data types, is we just need 2 tags. Okay, so let's make it drive 1 tell in, and it's going to be our drive 101 352 tell in. It does this right here. And we could see when it has all of the values and everything there cool for us, right? So if you notice this, in comparison to the way that we've done it in the past and making those 2 different sets, you can make it set up to where all of these values, all of these values are collapsible as well, because they're all built into a custom data type as well. And that's how you'll see some of my other videos. I have some about Telegram 352 on there. You'll see that. It's also in the custom Telegrams live stream, to where we go into how you can make whatever you want and put it in here. But yeah, so this works. And now we're gonna have drive 1 tell out. Now we need to address this to the input is going to be what was it, 256.0, because the first value of this is a Boolean. So let's just check that. Yep, 256. This is going to be Q256.0 because the first value is a Boolean. And that's all you have to do. Like, those are tied in now. Now you use these tags and they are sending that to that data. Now, how do we use that? First thing we're going to do, I'm going to show you, and I'm just going to do this in OB1. Again, if you are a seasoned programmer, a Siemens programmer, you want to be putting this into a function block or a function call or something that you can reuse. I'm just going to show you just the basics about how to convert these values and everything, because it's a little not necessarily straightforward. So let's add a default tag table, sorry, user constants, a no-op, and we're going to call it just a false. No, a data type. It's a Boolean. And the value is false. That way, I can do something like this. I can go. So when no op, I want to go through, and remember I said we have bit 10 needs to be on, and then we have those first 5, so it's like 2 through 6. So we have 6 values that we need to do here. So let's do this and go. What's up? What's up, action? Welcome to the stream. We're about finishing up. It's been at it for good night, 2.5 hours. But yeah, we're talking about drives 101. Just setting up kind of a custom little setup here. And honestly, remember, the way that we've done this, you can set these up for any Telegram type, even a custom Telegram type. And if you're wanting to do custom Telegrams and you're like, wait a second, custom Telegrams, you can do that. Got a whole live stream on it. Yeah, it's called Free Telegrams. And we talk a lot about it. So we got 1, 2, 3, 4, got 2 more. So, and so we're just going to turn on all of these and let's see if we can do it this way. So I always wonder, so I want my, nope, wrong one. Let's tell in, we won't tell out. These are controls. So first thing we want, I have this set up wrong. I didn't change the data type. So I forgot to change the data type because this is still a data type tell in. And the reason I did this, I was like, my control by PLC is not here. So we need to change that to a tell out, right? Now when we go here and click, is my head covering that up? No, good. So back over here, we can go here, Telegram out. Why did that not? It's not gonna like that. But why did this not? Alright, we're gonna click off. For some reason there it is, it didn't update. That's a bug. Yeah, so I'm using this little details view, and then you can just like drag stuff out of here sometimes. So control by PLC, oh no, it's not gonna let me drag it. So drive 1 tell out, control by PLC, and then we're going to do drive 1, tell out, continue ramp, drive 1, tell out, enable operation. So obviously we just want these on all the time, and so that's what I'm just going through. Yeah, his younger brother and dumber brother. I did get recruited to play football at Princeton. That's my claim to fame. But yeah, that's the only way I qualified to go, which, by the way, Albert Einstein was a professor at Princeton like a long time ago. The only way I qualified was I could run a 4.440. I did not qualify academically. So enable operation, enable ramp, and then now we got drive, tell out, off 2, and drive, tell out, off 3. All right, and so those are going to be on all the time. We'd save that. Yeah, and I'm normally in a little bit more relaxed, but yeah, today it's drives 101. So we're going back to school, and so the last thing that I would want to do is like the actual speed set point and explain to you how this value is calculated. Okay, so remember we talked about that reference value before. Let's go look at those real quick. So all your reference values are at parameter 2000, and so if you just click in the parameter number column anywhere and then you just type the number, it blink jumps you to it. And so parameter 2000, we want the extended parameters. So there's a little bit of like hand holding that goes on with the G120. In the S120, it defaults you to the extended parameters. In the G120, they don't trust you, and they give you the standard parameters. But because you're watching this channel, you know about the extended parameters. You know what to do. You can do it. So yeah, anyway, all of these values are these reference values. And so remember, everything that has an actual unit in the drive, everything else is in percentage, so it's in per unit. And so the way that you would say like to send a per unit speed would be like a percentage speed. So if you want to run your drive at 50% speed, and I will say a lot of times it is easier to set your machine up around per unit systems. So if you can get your operators used to saying, hey, I want to run at 30% instead of like, yes, the video absolutely action will be available later. I always have the DVD or the DVR available on this. So you can definitely catch up and watch everything. But so the per unit system is very good because it kind of immediately gives your operators, hey, if you're running at 70% speed, you might be pushing it. But if you're running at like 1200 RPM, what's that? What's 1200 RPM? Like, who knows? And so that's kind of why I think that they set this up and kind of like didn't hide the actual values behind, or they use percentage in everything because it makes the math easier. And ultimately, if you're using percentage, it kind of gives an immediate kind of like, oh, this motor is kind of, you're pushing it, you know? And so what that means though is everything, if you want an actual RPM value, you are going to have to scale it to some reference value. And that's what these P2000 reference values are. I changed the speed to 1800 RPM, and that is so that you can know that your set point, set P first, OINT, set point is going to equal your reference value. So you have to convert your reference value into a percent. Okay, so what you're going to be sending over to the drive is going to be a percent. So set point equals your, or sorry, this is going to be drive word. So what you're sending to the drive equals, yes, action. The video will be available later. Like the live stream, you'll be able to watch it whenever. Honestly, because of the international crowd, most of the people that watch this channel, that's why I kind of today I have a little bit of my Easter guys that were able to join in live, and I know it's kind of in the middle of the day and middle of the work day for people in the US, but yeah, so you will be able to watch it on demand later whenever you get home. And yeah, so so the drive word is going to be the set point divided by the reference. So that gives us a percentage. So that'll be like point something or 1 point something. And then that's going to be times 100 in order to, actually, no, incorrect. If you want an actual percent value up on the screen, you need to multiply that by 100. But this is going to give you like 50%, like a 0.5, 0.55, whatever. Set point divided by reference, and then times 16,383. And I'll tell you why. 16,383. Okay? So that is how that math is going to work. And so we can do a calculate block. Let's just do it this way. Click here, do calculate. And so we're going to do all this in real because we need, and then we're going to need our set point. So we have 1, 2, 3. So this is 16,383.0. And this would be divided by reference. So this is going to be our reference speed in the drive, 1800. And this is going to be drive like this. And obviously I don't have that tag made, so for now I'm just going to do this. I do this way too much. This is bad habits. You need to have a block. You need to have a data block where all of your stuff is. Always kind of joke around that if I see this in a program, I know that you come from Allen Bradley because that's how you do it in Allen Bradley. But if you're coming from Allen Bradley, you can do it the way that like you're used to, going in and setting it. There just are better ways of doing this and organizing your data in Siemens. So set point divided by reference. So N1 divided by dot question mark divided by N2 times N3, and then our output. I don't think it will be able to do a direct conversion to it, but let's see. So let's do drive tell out. Maybe it will. Yep, it does. So it converted from real to int. Now it says there might be some errors, but yeah. So that's actually all you need to do. And now drive on. And then what you could do now is have a little bit that is drive 1 start. And we'll define that tag, global memory. And then we are going to set an output, drive 1 tell out. Off one. And then there you go. That is literally all you need to so this is all you need to do to actually control the drive. Now you would want like acknowledge faults and things like that, and you could bring in, but you see how now all of your data is available in your these tags, and you can also tie these as well. The way that I do this with the tags, you can tie them directly to memory, which is nice if you're not having to use like a what's it called, if it's kind of a one-off project and it's not like repeating all the time, because you'll always have to create these tags and tie them in somehow. But you could totally set up a function block that has an input of this data type, and it'd be totally fine and it would work, and you could have your custom block. And honestly, we'll be building some of those, but as for right now, yeah, here is the basics. So you turn on all the bits that you have to have, and then you give it a set point, and this is in Drive set point in RPM, so you could set this to be like 1000 RPM, and because of this conversion, it's going to convert into this. And let me talk about this value. I told you I was going to talk about this for a second. So action, there aren't a lot of, while I'm getting this changed over to this, I want to talk about, Action had a question about if there is some material that is good for the S120 training, and there's really not many books available. I have a lot of videos on this channel that deal with a lot of the S120 topics. S120 in particular is a huge kind of like ball of wax. You can do all sorts of different applications. I have multiple streams where I go through and set up different S120s. I think probably the best one that you would want to do would be to watch the designing a winder live stream, and it has a lot of information that's available specifically about the S120 that has a lot of like the detailed stuff for the S120, but in terms of like books, not so much. I'm trying to kind of fill in that gap here with these types of live streams that are a little bit more customized, that aren't just like, oh, here's this very specific case. So if you have specific questions, feel free to ask your questions in the comments, and I will go through and probably make a video about it. Also, we do have a Discord that there's an automation, there's a help desk channel, and then there's an automation channel. If you have a specific question about, hey, I'm having this problem that I'm working through, drop it in the help desk. We'll get some of the guys that have experience in that. We'll kind of touch on it. And if you're just kind of asking general stuff about S120s or whatever, like how to, like what drive, what topic to use or whatever, drop that in the automation channel and we can kind of go that. But the Discord link is in the description of this. And yeah, it's open to anybody to be able to come in. If I see your comments and things like on the stream, I'll upgrade you to like a chat veteran, and then you can kind of like gain access to the voice channels and things. But yeah, that's what I'm trying to do. I'm trying to give a little bit of resource for some kind of like at your own pace learning for S120s and SINAMICS. Well, let's talk about real quick. I've got about 20 minutes, not even 20 minutes. I got about like 15 minutes. I want to talk about the reason why that number, that 16, let me do this. The reason why that number is 16,383. So you might notice that is one of these base 2 numbers, right? So base 2 numbers, binary numbers, that is a 14-bit, that is the maximum that a 14-bit binary number can actually hold. So Why 14 bits? Well, 16383. So you have 0 to 2 to the 14. Sorry. So it's 2 to the 14 minus 1. That's what that number is. So it's 0 to this maximum number. And so that's what that is. So that's a 14-bit number. Well, you're like, well, Jason, we have 16 bits there. Why can't we have the full max 68,000 or whatever it is? Well, first we have a sign, because the set point, the most significant bit, the 16th bit, is taken up by the sign. So we actually are having we're trying to do plus or minus our value. So if you put in a negative set point, the motor will run backwards. Okay. If you put in a positive, it will run forwards. Cool. So that's what the first sign is. So we're left with 15 bits. So why don't we get the 32,000 that kind of like we do in other things? Well, we actually may want to command a set point over 100%. And we kind of talked about a situation like that earlier. You might have your reference value set to 1500 and you're going to scale that to 1500. Well, what if your motor is, you're able to go up to 60 hertz and you're within the ratings on that? Well, you would command 110%. So the math that we just kind of talked about, if you had your scaled value, say your reference value was 1500, well, yeah. So I'll answer that question. There's a question about kind of like the function blocks and things that we're using. So if our reference value was 1500, like we have here, and we wanted to command an 1800, and we wanted to command a 1800 RPM, and we did the same math that we just did over there, what we would do is we would do 1800 divided by 1500, and that's going to be greater than 1, right? So that's greater than 1, so that's going to be like whatever that is. So that would mean that we would be multiplying this times something greater than 1, so it would get bigger. And so we need that extra space in order to command up to 200%, because we might want to say, hey, run at 120% speed. Or you're like, hey, your current is 150% of your rated current. And so you would need to be able to have these values. So that's what that 16383 is. So all of your values going out to and coming in, other than the warning, the fault and warning values, all of those values are scaled to this 16383. So all your set points and actual values values are 0 to 16383 equals 0 to 100%. But it's actually plus or minus, and then you can go plus or minus up to 200%. So you can actually send it a 30,000, for example. And so that's going to be like the decimal equivalent of that. So that's the explanation of the set points and how to scale them. So remember, it's, yeah, if you're trying to scale it to an actual value, you have to use those P2000 reference parameters and whatever you're scaling them to. And that really comes into kind of that user data. And we're kind of have a chatter here asking a question about for universal control is based on the telegram that we're using, or rather the drive or the motor. So in the universal kind of state, so we'll make a little bit of a point. We'll go back up to this real quick. I've got about 10 minutes that we could talk about this. But there are other telegrams here. And so a universal motor, these telegrams, if you look at, well, I guess I could do it from this page. So any telegram that is less than 100 on a Siemens Drive is going to be what is an industry-specific telegram. So Telegram 1, Telegram 20 are both going to be industry-defined telegrams. And so any manufacturer that uses those Telegram 1, 2, 3, 5, 20, like all of those are all going to be the exact same. So if you're defining a function block and you are intending to make it available for other manufacturers, you would want to use that those standard telegrams, anything less than 100. And so I think I don't have time to pull it up now because I didn't have it prepared, but there is a document that details out all of the available telegrams, and there's the list manual for whatever drive you're using. The list manual will have the available telegrams, and the Siemens drives will obviously have like 352, 351, 111, 112, telegrams like 750, like all these other Siemens specific telegrams. If you're wanting to make a universal function block that controls a universal drive, use a telegram that is less than 100. And I really want to say that most of them are going to be, you're probably going to end up using like a Telegram 3 or 5, because I think those have position feedback in them, Telegram 3 and 5. And so if you're really wanting to do universal control in a function block, those are going to be probably the easier ones. Cool thing about it though is most of the control words and the status words, so like these first parts of our blocks here, so like this is the status word, those are pretty much going to be the same. Like they are basically the same even in the Siemens like oddball telegram things. If you're really wanting to make a truly universal function block, there may be a way that, because like there's I mentioned the SINA 352 block. I had one of the users that was kind of asking about it and kind of brought up like how to use that block, and it has user data built into the inputs. So where in my block, I can send it this user data here. Oh, don't do that. I can send like this user data here. Just build that into a block, and honestly, you can set like configurations in your function block, and this would probably be more of like an SCL defined block, to where you set, hey, this is this manufacturer using this telegram, and it uses the different types, and basically you have your block can input in all of the data, and that's how I would probably do it. If you're just wanting one block that you drop in everything that's available for any block, that's how I would do it. Because like for example, this Telegram 1 can run like volts per hertz, and it can run like volts per hertz and vector and servo, but it's only a control word and an actual speed, and then a control word, a set point, and then a status word and actual speed. So it's really limited. Once you get outside of those, there's like the Telegram 3, for example, is only available in servo control because it has to have a position feedback. And so you can't use a Telegram 3. Well, I say that you can't. The information that is in Telegram 3 will overlap if you're doing a bunch of Telegram 1 drives. Whereas, yeah, so the Telegrams, you can run into a problem lining those things up if you're not kind of regulating the address space. So there would be a way to make, based on the hardware IDs, a block to where, okay, I put in the hardware ID of my drive, and then have a way that it says, oh, hey, I can see that address space, how big that address space is, so I'm going to use one of these telegrams that has the proper address space. You absolutely could do that. It would be a little complicated. Probably the easier way to do it would be to make a Telegram 1 block, a Telegram 3 block, a Telegram 5 block, Telegram 353 block, and then just put them all into a library, and then you just pull out, hey, I'm using a Yaskawa Telegram 1, and then pull out that, and then if you brought in an S120 later that had all Telegram 105s, then you just have that block that you just pull in. That, I think that's probably a better way of doing it. It's not completely like single firmware type application, but if you're wanting to go like an actual single universal block, there is a way to do it, and you would just have to look at the hardware IDs and then limit your tags on that. Well, everyone, I have got to go. It has been a great time. I probably pushed a little bit outside of what I would consider a 101 class for this, but I think that at some point you're going to be able to get the information that you need. If you're just joining in, like with drives, and you're just starting your automation journey, this is a great place to be. Hopefully we're building a lot of resources that can help you out on all of this stuff. And yeah, if you've made it this far, thank you so much. Hopefully you've already hit that like button on the stream. And if you're not subscribed, check to make sure you're just subscribed. Sometimes the algorithm will just put my stuff into your feed and you don't even realize you're not subscribed. And maybe you'll miss out when I go live and things like that. So if you would want to be notified about when I go live, definitely ring the bell on that to subscribe. And the last thing I want to talk about, again, we've got the book that a lot of this material has been pulled from, at least the first half of it. Again, this was written by my dad for the most part, and then co-authored by myself. And no, my dad was not Albert Einstein, but he is really smart. He probably could challenge Einstein in some place. But all that to say, building some resources, we built up the community to where hopefully by the next stream we should be offering memberships. One of the things that I wanted to offer to you in memberships would be all of the stuff that we create on stream. I want to be able to let you have that and like motivate you to kind of be able to have a little skin in the game on stuff. And so we're planning on 2 different membership levels. One would just be kind of like this data types that we made. Those would be in an archive every week. I would also link in all the documents and all that stuff. And plus you get the regular like chat swag and stuff like that to kind of like flare up in the chat when you're here. But then there'd be a second level membership to where a little bit more that you would actually get these files to where like if you wanted to set them up and then have actual the project files themselves, you would be able to have access to that. So hopefully by next week we'll have all of that set up, but be on the lookout for that. And yeah, Thank you so much for being part of this community. It's been so awesome. Like, just over the past few months, growing it into something that is reaching around the world. I love the fact that every stream we have almost anyone that's awake from any time zone that's awake is eligible to be on this stream, and I absolutely love it. I thank you for supporting it, and hopefully it is beneficial to you. But I gotta get on. I've got to get on to a meeting here in 2 minutes. But yeah, thank you so much for joining. And again, like and subscribe, and should see you like probably tomorrow. Probably gonna be doing one of the design and chill mechanical streams again tomorrow. But yeah, next time I see you, I'll see you. Thanks for joining. I'll see you.